All right, so this next chapter, I've broken it into two parts. So this first part is going to be on your next exam, and then the next part is going to be on the next exam. The first part that we're going to get into of carbohydrates is really kind of your foundational parts of carbohydrates, like lots of the terminology of your simplest carbohydrates. Um, your learning objectives for chapter number 8, basically the first 7 of these are going to be what we cover today or in this lecture, and then the remaining 5 are going to be in the next lecture. So a carbohydrate is a polyhydroxyl aldehyde or ketone, or a substance that yields such compounds upon hydrolysis. So the more common names for carbohydrates are ketoses, or a ketose or an aldose. Um, Now, when you look at these compounds, one of the most important things that you need to do is to identify your functional groups. And the great thing about this is that your functional groups are highlighted and they're presented in magenta. So there's your aldehyde and there's your ketone. Um, Polyhydroxyl, well, hydroxy or polyhydroxy, 1, 2, that's more than one, so that's poly. Um, so though they're kind of self-explanatory in that respect. A great question is, are these soluble in water? They are. They are going to be soluble in water because if you look at these functional groups right here, hydroxy groups, what do they love to do? Or what do they have? Lone pairs of electrons. So these are compounds, or these molecules are going to be able to participate in hydrogen bonding. So that's going to make them a little bit more soluble in water. Now, um, a substance produced by plants or produced in plants by photosynthesis is 6CO2 combining with 6H2O to produce C6H12O6 and 6O2 molecules. This right here is a glucose molecule, or most commonly you'll see this known as glucose, but as we'll see today, C6H12O6 is not simply glucose. Sugars are burned by cellular respiration, cellular, LAR, respiration, or simply respiration in cells for energy. So C6H12O6 reacts with O2 to produce CO2 and H2O. Now, 4 important functions of sugars in living systems. They are energy stores, they are metabolic intermediates, a sugar of DNA and RNA. Ribose is that sugar. It's either ribose or deoxyribose. They are structural elements of plants and bacteria, and sugars are involved in cellular communication. Now, monomeric units, sugars or monosaccharides linked through bonds known as glycosidic bonds or glycosidic linkages. I'll use that term glycosidic linkage. I don't know why, but whenever I say glycosidic, linkage is the term that follows, even though linkage is interchangeable for bonds. Your most common sugars are trioses, tetroses, pentoses, and hexoses. So these are sugars that have 3, 4, 5, and 6 carbons. There are 2 general categories of sugars. They are aldose. They have an aldehyde group, and a ketose. They have a ketone group. Now, one of the things that's important to understand about any sort of aldose and ketose is when you're counting up your carbons. So what I've got down here, well, this is an aldose because it has an aldehyde functional group. It has 1, 2, 3, 4 carbons. So this is an aldo tetrose. Now, over here we have 1, 2, 3, 4, 5. This is a keto pentose. So when it comes to sugars, it's important to be able to classify them and understand basically the organization. Something can be a pentose and be a aldose or a ketose. So we'll get into the different sugars in a little while. Now, the stereochemistry of carbohydrates. Fisher projections of carbohydrates have a carbonyl carbon at the top. Fisher projections are the most common sugars, or the common depictions of sugars that you'll see in basically any biochemistry textbook. If you look at these on the right here, this sugar right here on the left is L-glyceraldehyde. On the right, it's D-glyceraldehyde. It's appropriate that these are on the left and right because of the fact that these are both 1, 2, 3, 1, 2, 3. These are both aldo trioses. But what makes these two different from one another, well, sorry, let me take a step back. They're both aldo trioses, and they are both glyceraldehyde. So that common name, glyceraldehyde, is an aldotriose. What makes these sugars different from one another is one is L and one is D. And the positioning of this hydroxide group, is it on the left-hand side of my sugar or is it on the right-hand side of my sugar? By virtue of this hydroxide group being on the left-hand side, this is L-glyceraldehyde. This hydroxide group being found on the right-hand side of my structure makes this D-glyceraldehyde. The hydroxyl group, so that is the single hydroxide group on a chiral carbon in this structure. Now, with that in mind, there's a couple of different ways that you can describe this. So in every single sugar, there's going to be one hydroxide group that is going to have the sugar being designated as a D sugar or an L sugar. The hydroxyl group on the chiral carbon farthest from the carbonyl group determines whether the carbohydrate is an L or a D. Now, if we take a step back, this says the chiral carbon, okay? Well, you have to be able to identify a chiral carbon. So when you think about a chiral carbon, or whenever I think about a chiral carbon, I think about a carbon that has a total of 4 different groups on it. So that's 4 different groups. So if we're looking at this right here, H, H, OH, CH3. This would not be chiral because 2 of the groups are identical. Now, if we look at an aldehyde functional group, well, does this have 4 different groups coming from it? It doesn't. It has 3 groups coming from it. So then if we look down at this carbon right here, this goes to CHO, goes to H, it goes to a chain, and then it goes to an OH. So that's 4 different groups. So this carbon does go to 4 different groups. So this is a chiral carbon. This carbon right here does the same. It is a chiral carbon. This carbon right here, well, 2 of the groups that this goes to are hydrogens. So this is not a chiral carbon. So when you look at a aldotetrose, this is a molecule that has 2 chiral carbons. Now, to identify if our sugar is an L or a D sugar, we need to identify the chiral carbon that is farthest from our carbonyl carbon. So here's where our carbonyl carbon is. This is a chiral carbon. This is a chiral carbon. This is the chiral carbon that is going to designate us as an L or a D. We've got our hydroxide group on the left-hand side. So this is L. L, what's the common name? Erythrose. This one on the right-hand side, well, that is a D sugar. Now, so look to that highest numbered chiral carbon to determine if you're talking about a D or an L sugar. Now, if we proceed from here, this gives us a nice display of all of the different sugars that are aldoses and that are kind of important for you to know. Now, whenever I'm looking at sugars, one of the things that I think about is, well, we learn about sugars from a metabolic standpoint for the purposes of metabolism. We learn about sugars for the purposes of um, biological relevance. So when you think about all of these different sugars, you have to think about which are the most biologically relevant. And that's how we arrive at galactose, mannose, glucose, ribose, erythrose, and D-glyceraldehyde as the sugars that you need to know. Now, these are all, like I said, displayed as D sugars. Now, one of the things that I'd like to do is I'd like to show D ribose, and I'd like to show you L ribose. So if you look at D ribose, we know that this structure is D ribose, in part because it has the label, but also our highest numbered chiral carbon has a hydroxide group on the right-hand side of our structure. If I wanted to draw L ribose, what I would do is I would make my chain of 5 carbons. 1, 2, 3, 4, and 5. H2OH. And this is the way that I try to draw sugars. I will always draw my functional group, my kind of name declaring functional group, my aldehyde, because I know that this is an aldose. Then my carbon number 5, my non-chiral carbon. So essentially what I do is I draw my chiral or my non-chiral carbons. Then what I'm going to do is I'm going to say, am I drawing a D or an L sugar? I'm drawing an L sugar. So on my last carbon, or my last chiral carbon, I'm going to put my OH on the left-hand side of my structure. Okay. Then, since I'm translating this structure right here into an L form of ribose, what is important for you to know is that the positioning of all of these groups must be the same if I'm drawing L ribose. So if I'm drawing L ribose, then what I need to know, my hydroxide groups need to follow. These hydroxide groups are all relative to one another. So if I'm drawing L ribose, well, then I have to put my highest numbered chiral carbons hydroxide group on the left-hand side, but the other hydroxide groups have to be on the same side as that right there. So essentially what I'm saying is if I drew this structure right here, okay, that tells me I've drawn a L sugar. Here what I have is hydroxide groups on carbons number 2 and 3 that are on the opposite side of my structure as the sugar, as the hydroxide group that defines this as an L or a D sugar. So essentially, this sugar that I just drew right here is L. And then let's look at my other sugars. Where do I have my L or D sugar on one side and then the other hydroxide groups on the other side. Well, this would be L-lysose, because carbon number 2 and 3 have hydroxide groups on the opposite side as carbon number 4 has. This is an important part of understanding L versus D. It's not simply repositioning one hydroxide group. It's repositioning one to designate it as an L or a D sugar, and then the others that follow. Now, with that said, I want you to know all of these 6 structures. D-glyceraldehyde, L-erythrose, or sorry, D-glyceraldehyde, D-erythrose, D-ribose, D-glucose, D-mannose, D-galactose. I also want you to be able to flip-flop between D-galactose and L-galactose, should I ask for that. Now, if you look at these sugars right here, identify them as a D or an L sugar. This is definitely a question that you'll have on your exam. Well, this is carbon 1, 2, 3, 4. Here's my carbonyl carbon. This is an L. It's my carbonyl carbon. This is my chiral carbon. This is a D sugar, carbonyl carbon, L sugar. Now, with that in mind, this is like, it's a lot of information right here, but it's important information because I love this structure because it's shown in a hierarchical fashion. That is a word that I will always struggle with. No, I won't. I struggle with it right now. Hierarchical. It just feels like my tongue is going to trip out on me. Okay, so this is displayed, our umbrella term, isomer. These are molecules that have the same molecular formula, but different structures. There are constitutional isomers, there are stereoisomers. Constitutional isomers differ in the order of attachment of atoms. So glyceraldehyde and dihydroxyacetone are constitutional isomers. Great. They both have the formula of C3H6O3, but the order of attachment differs between them. There are also stereoisomers. Atoms are connected in the same order, but differ in their spatial arrangement. Underneath that term, there are enantiomers, which are non-superimposable mirror images. So a D sugar and an L sugar of that same thing are examples of enantiomers. There are diastereomers. Diastereomers are isomers that are not mirror images. So in this case, we use D-altrose and D-glucose. We jump back a page or two. Here's glucose. And here's altrose. Here's another look at D-glucose and D-altrose. Now, what is really helpful for me when it comes to knowing sugar structures is I come up with sort of a simple pattern for myself. And I look at sugars and I imagine, where are my hydroxide groups, or where is everything arranged on carbons 2, 3, 4, 5. I don't care about 1 and I don't care about 6 because 1 is where my functional group is and 6 is not a chiral carbon. And this is, of course, with aldoses. Okay, so if you look at then underneath are diastereomers, epimers. These are sugars that differ at one asymmetric carbon atom. So these are sugars that are identical, but there's one carbon or one hydroxide group different. So if we look at carbon number, let's start with carbon number 5 for these two structures. Carbon number 5 for D-glucose and D-mannose, they both have hydroxide on the right-hand side of my structure. 4, hydroxide on the right-hand side of my structure. 3, hydroxide on the left-hand side of my structure. 2, well, glucose has hydroxide on the right-hand side, whereas mannose has hydroxide on the left-hand side. These two sugars, glucose and mannose, are known as C2 epimers of one another. Now, another example of a pair of diastereomers are known as anomers. These are isomers that differ at a new asymmetric carbon atom formed on ring closure. So these are an anomeric pair of sugars are an alpha and a beta version of a sugar. Alpha D-glucose and beta D-glucose. These two sugars are anomers of one another. The difference between them is this right here is carbon number 1. That's significant because that carbon number 1 is this carbon number 1 right here. Just I'm showing a linear sugar. Carbon number 1, well, heck, we can just use glucose as our example. Carbon number 1 in glucose, that's not a chiral center. But suddenly, when the sugar cyclizes, excuse me, then it becomes a chiral center. And the positioning of the hydroxide group on that new chiral center, is it up or is it down with respect to my ring? So is it pointed up or is it pointed down? If it is pointed down, it is the alpha anomer. If that hydroxide group is pointed up, it is the beta anomer. Now, the sorts of questions that you should expect from these are, I'll give you two structures of sugars, and I'll ask you what their relationship are. Are they epimers? Are they anomers? Are they diastereomers? And when you look at them, think about anomers. In order for a sugar to be an anomer, or for sugars to be anomers, they have to be the cyclic form. They have to be a ring. So a linear form of a sugar, that's not going to be an anomer. Now, epimers, the important distinction when you look at two sugars as anomers, or as epimers, I'm sorry, is that the only difference is a single hydroxide group on a carbon. So if you see multiple differences, you're not talking about epimers. They're diastereomers, but they're not epimers. Okay, so that's why if you look at glucose and maltose, if you look at maltose, hydroxide on the left-hand side, whereas glucose has it on the right-hand side. Okay, so if that was the only difference, these two would be epimers. But carbon 3, we've got a hydroxide group on the right-hand side of maltose and a left-hand side of glucose. So that would be two differences. So these two sugars are not epimers of one another because they differ about two different carbons. Now, this is the important thing about forming rings. And your sugars are definitely going to cyclize because that's how they're going to function in a biological system. But essentially what you need to know about ring formation is that aldehydes and ketones will react with alcohols to form hemiacetals and hemiketals. I always like to think about these, and this is my second movie reference in just a minute, but if you've ever seen the movie Joe Dirt, if you haven't seen that movie, don't worry, you're probably a better person. I'm being facetious when I say that, but anyway, it's not highbrow humor. So in order for a ring to form, you have to have an alcohol, which let's think about aldehydes and ketones, or aldoses and ketoses. These are also known as polyhydroxy. Yeah, so we've got multiple alcohols, so we're good there. And then we have a carbonyl carbon in our aldehyde or in our ketone. We're good. So these can definitely take place. Now, what is this going to look like? Well, if we take a sugar like glucose, glucose can form a 5-membered ring or a 6-membered ring. What's more likely to happen is that, well, this carbonyl carbon right here, carbon number 1, which I'm circling right here, will react with the hydroxide group on carbon number 5. So here is that hydroxide group. Here is that hydroxide group. And that is going to, so this oxygen is the oxygen from my hydroxide group on carbon number 5. This oxygen, by comparison, or this hydroxide, well, that is our carbonyl oxygen, which picks up a proton from the environment and is going to either be the alpha or the beta anomer. Now, one of the things that I always love to bring up is we bounce back. We had to have an alcohol react with an aldehyde. This is an alcohol, 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 alcohol. So when I look at glucose, what ring sizes are possible to form? And I'm going to erase some stuff here. We need carbonyl carbon of an aldehyde. We've got that. So this could be one, this carbon could be a member, this oxygen would be, or sorry, this carbon could be a member of our ring. This carbon could be a member of a ring. And then if this carbon reacted with that oxygen, we could theoretically form a 3-membered ring. This oxygen being, so I'm underlining the members of this ring. So we could form a 3-membered ring, okay? Then this carbonyl could react with, oh, sorry, wrong side, this hydroxide group. So we could have 1, 2, 3, 4 members. So we could form a 4-membered ring. Alternatively, this carbon could react with this hydroxyl. So we could have 1, 2, 3, 4, a 5-membered ring. We could have this carbonyl react with this hydroxyl. So 1, 2, 3, 4, 5, and 6, as we are talking about, a 6-membered ring. And then we could even have this hydroxide on carbon number 6 react with carbon number 1, so we could form a 7-membered ring. Now, I always like to bring this up because it's a question of, is this possible? The answer is yes. But then we have to narrow our scope and think about, but what are the chances that it happens? If you think back to the structures of rings from organic chemistry, well, maybe the most common rings are 5 and 6 members. Can you form a 3-membered ring? Yep. 3-membered rings are super stressed. 4-membered rings, a little bit less so. 5-membered rings, well, they're certainly less stressed than 3 and 4-membered rings. My point is that, yes, a 3-membered, 4-membered, and 6-membered, and 7-membered ring could form. The likelihood that it happens is fairly low. So 6-membered rings, which are pyranose or pyranoses, and 5-membered rings, which are furanoses, are going to have reactions between our carbonyl carbon and a hydroxide group on one of the other, or one of our carbons within the ring. And the hydroxide group, the alcohol is going to produce the oxygen that is a member of that ring. So a furanose is the result of carbon number 2 reacting with a hydroxide group on carbon number 5. Now, what's important to recognize is that these structures that I'm showing you here, the linear and the ring forms, these are the ones that I think are easiest and most palatable to draw. I think that you should be comfortable drawing this. These are not the most realistic because, one hand, I mean, these are all drawn in 2 dimensions. And everything in a cell exists in 3 dimensions. Well, with that, the real geometry of a sugar is it's going to take on the chair conformation. And sometimes they'll take on a boat conformation, but they're typically going to take on that chair conformation. So this gives a bit of an idea of perspective. Now, what that means is our hydroxide groups are able to hydrogen bond, and they can hydrogen bond with different things kind of throughout space. The ring formation of glucose, one of the things that I think is important to recognize is that glucose, D-glucose, in its linear form, it's going to be about 1% in an aqueous environment. And that is really very, very transient or temporary, because typically what you're going to have is you're going to have about 64, 65% of the ringed glucose as the beta configuration, because that puts your new anomeric hydroxide group in the equatorial position as opposed to the axial position. Whereas the alpha puts it in the axial position, meaning it's a little bit less stable, or not necessarily stable, but a little bit more sterically hindered. And so there, with all of that said, though, this is an equilibrium. All three of these things are kind of in equilibrium with one another, because the linear form of glucose will cyclize. The cyclized form of glucose will undergo a phenomena or process known as mutarotation, in which the ring opens up and this hydroxide group will rotate upward, and then the ring will close again. And then the same thing, the beta form will convert to the alpha form. So this interconversion from the alpha and beta forms of our sugars is a process known as mutarotation. Now, with that said, the sugars will cyclize. Sugars will also they are ripe for modification. There are molecules known as glycosidic bonds, there are linkages known as glycosidic linkages. These are basically using some of these hydroxide groups and making a modification to them. Alpha D methyl glucose. That's where we put a methyl group on our hydroxide group, or in place of our hydroxide group. We form an O-glycosidic linkage. Adenosine monophosphate, also known as AMP. Well, that gives us an N-glycosidic linkage. Guanosine is another example of a molecule with an N-glycosidic linkage. And basically all of these different compounds are going to have an N or an O-glycosidic linkage, or in some instances where there will be a sulfhydryl group in place of that OH group. And that would be an S-glycosidic linkage or an S-glycoside. Now, glycosidic linkages, and this right here, methyl glucose, I want you to think about that in preparation for our discussion of polysaccharides, or oligosaccharides, sugars that are multiple sugars assembled into one complex molecule. All right, well, that is all. I hope this is helpful. I hope you have a better understanding of sugars, and I hope you have a